All right, so let's get to it. Let's talk about typical requirements and design considerations. So here is an overview slide for the ADCS system. And we have requirements in the context of this larger subsystem. So here in the middle, we have our spacecraft. It is subject to internal disturbance torques and external disturbance torques like atmospheric drag, gravity, magnetic field, solar radiation pressure. And it needs to sense different reference cues to get attitude. It will pass measurements of attitude either directly to an onboard computer, which will come up with algorithms to estimate attitude and control actuators, or another architecture is to send your attitude measurements to ground control, and there, on ground, the attitude will be estimated and attitude control commands could be generated here on ground and sent to an onboard computer. So this path short circuits the job to have the spacecraft be more intelligent. This path towards ground control is less intelligent, like teleoperated controls. Anyway, then the torque commands are sent to actuators, and actuators impart torques onto the spacecraft. Now, this process is all towards the goal of these different attitude requirements. They could include pointing the antenna towards Earth, pointing the thruster in the thrust direction, say to change your orbit, pointing your sensor into a target direction, or pointing your solar arrays toward the sun. Some mission-derived requirements. Of course, there is the obvious size, weight, and power, but specific to the attitude determination and control subsystem, we care a lot about pointing accuracy and pointing precision. So this usually comes from, we'll talk about this later, but things that want to be pointed in the previous slide: antennas, thrusters, solar arrays, payload sensors. So with these different components in the different subsystems, they want a certain pointing accuracy and pointing precision. And I want to make the distinction here between accuracy and precision. Say you want to get to a certain reference value. So let's say that I want to point perfectly nadir equals 0. So my reference value would be 0. My pointing performance would be at the expected value or mean of this probability distribution. And your accuracy would be that difference between the performance expected value and your reference value. Your precision is the degree to which you can repeat or reproduce measurements or performance. So it's like this, this spread. So accuracy is difference between reference value and expected value. Precision is how precise, what standard deviation you can control that or measure within. Other mission-derived requirements could be agility, which is your ability to move quickly, which includes rapid retargeting, fast and transient settling, and low jitter pointing control. So one way to demonstrate it is this picture of a system without a control moment gyroscope, which is a highly agile actuator. You'll see the satellite can point at this target and over time along this track, this target, and on and on. But with a control moment gyroscope, you can point at many different targets because you can slew much faster. Different kinds of pointing strategies could be that you are targeting a collection of points. You could be doing strip mapping, which is a different type of maneuver. You can be coordinating stereo or tri-stereo with a collection of satellites. You can also do a maneuver called corridor acquisition. So all of these different types of maneuvers impose different kind of agility requirements or characteristics on your control subsystem. Now, what is drift? Drift is a system behavior where control system slowly integrates error and drifts away from desired orientation. Drift can also be an accumulation of sensor error. So here is just a very, it's a generic depiction of drift where residual is some error. And at the beginning, your error can be 0, but let's take the example of an IMU. A gyroscope within IMUs can cause the attitude estimate to drift if instead of measuring 0, like it is supposed to, like the spacecraft is assuming, you measure a tiny non-zero angular rate. You can, if you measure this bias and you integrate it over time, then you're accumulating a non-zero angular attitude estimate over time. You can correct for this drift by trusting an independent reference cue, with an independent measurement coming from, say, a star tracker. A star tracker differs from IMU in that star trackers lock on to a measurement provided by the celestial sphere, which is constant and steady. Drift can also come in the form of control, like this bullet point says, where let's take high tie as an example. Within high tie, there's a cryocooler which applies some non-zero torque to the system persistently. There are these pistons within the compressor that oscillate and create friction and torque from that friction. So you can imagine drift as if your system was static before the cryocooler was turned on, and then you turn the cryocooler on, the system will accumulate angular momentum and start to rotate with some increasing angular rate. So the question down here is, when we talk about drift, does this mean we want the drift control to be high? This way the satellite doesn't leave the desired orientation. So I don't know if the language here, drift control to be high, is what I would use. But it is true that we don't want the satellite to leave the desired orientation. So to compensate for drift, we have these two methodologies of making sure your sensor estimate, your attitude estimate does not drift. So I just gave you one mitigation strategy. And you also want to make sure that your control compensation also does not drift. So instead of just having a mitigation strategy for that is, instead of just trusting that your spacecraft will be at 0 angular momentum, you measure your angular momentum frequently, and then you compensate for it through, so it's like real-time feedback control instead of open loop control, which is you just set it and then you go. Mitigation strategy is to not trust that it's set, but to keep a careful eye on it and sample periodically, control periodically. Okay, other motion-derived requirements could be motion constraints. So this could be maximum thresholds for your attitude and derivatives. The reason why we have motion constraints is because there could be sensitive components on board, like flexible appendages, which if you give a spacecraft with, say, a long boom, some kind of angular rate, then that appendage is going to start to bend. At some point, if you rotate too quickly, then the appendage is going to snap. You can also bound motion by vibration-sensitive components. So what are some examples of vibration-sensitive components? Are they something we might need to worry about for our spacecraft? And yes, we should worry about it because there are vibration-sensitive sensors on our satellite. So vibration-sensitive components could be detectors on board. For example, some IMUs don't like to be impacted. Remember, there was a lecture we had for space environment where we talked about impact. So similar ideas here. Vibration sensitive components don't like a lot of jitter. Vibration can also inspire resonant frequencies that cause a high enough amplitude of oscillation or high enough energy intensity of oscillation that you can damage sensitive components on board. Let's see, what other things? So maybe we'll talk about maneuvers that are rate limited, acceleration limited, or jerk limited. These are maneuvers that have motion constraints. So on the right here, we see an example of a position limited, rate limited, acceleration, and jerk limited response, or trajectory, sorry. This is something you set out to track. So here the position is limited to below P7, where you start out from P0 and you ease into P7. Now the reason why the position, we can call it attitude, it's just a generic profile. The reason why this attitude profile looks like so is because within these regimes, the derivative profiles have been defined. So the velocity here looks like so, where the maximum velocity occurs between V3 and V4. This is the angular rate. This is the rate limited, where capital V is the limitation on rate. Your acceleration profile is going to look like so, where your acceleration is limited by capital A, and it occurs at V1 to V2. And if we get down to our highest derivative, you see these binary steps of the amount of jerk in each time period. So in T1, we have capital J amount of jerk, which is, you can think of jerk as intuitively the physical snapping of motion. So I hope that attitudes, rate, and acceleration are intuitive to you. Jerk is the derivative of acceleration, where you know when a car goes from a stoplight to accelerating, when you're at the intersection and the driver starts to accelerate, you can feel that, like, right, your head jerking backwards into your seat. That's the intuitive feeling of what a jerk means. So anyway, jerk limited, that is something that, you know, in a car, our heads don't like to be jerked. In a spacecraft, there are components that also don't want to be snapped back. So that's why we have these types of motion or rate limited, acceleration limited, or jerk limited maneuvers. Question, with the limited amount of propellant brought to space, it's actually the structural limitations that govern how fast things can move. So yeah, this is a nuanced question that I want to dig into. Good question. There are multiple variables that dictate the maximum rate, acceleration, or jerk the spacecraft can experience. Moment of inertia from the structure, so structural limitations, can be a limiting factor, but more importantly, the specifications on your actuator will limit your angular rate, your acceleration, and your jerk. For example, the maximum angular momentum of your reaction wheel divided by your moment of inertia will be your maximum angular rate. Your reaction wheel's maximum torque divided by your moment of inertia is your maximum acceleration. So yes, structural limitations can be one limiting factor, but I think the dominant limiting factor is a characteristic of the actuators that you choose for your system. Okay, other emission-derived requirements include sensor and actuator placement and orientation. We already went over this in a previous slide, but do remember, some things want to be facing the space environment and some things want to be really inside the body and want to be oriented in certain ways. Another emission-derived requirement is reliability. So the ADCS system gets called out for reliability more so than other systems. Structures could be another system that gets called out because actuators or moving parts can fail due to wear and tear. So for example, we've been talking about reaction wheels, which are these little rotors that are spinning. Two of Kepler's 4 reaction wheels are shown here, where one of the wheels has an elevated amount of friction due to just, wear and tear. Maybe the lubricant is displaced or not present anymore. Maybe there's some ionizing dose that has zapped out or evaporated. Parts, sorry, there's a trash truck outside. I'm just gonna pause for 1 second. Okay, sorry. So yeah, regardless, reaction wheels can fail over time. There's a lot of mechanical motion that's inside, there's a lot of friction, and so the lubricants can disappear or the structure itself can wear down, causing abnormalities within and then causing it to fail. It could also be that radiation causes sensors or anomalies within materials to fail. Okay, so those were mission-derived requirements. Now let's look into the way that the other subsystem functions interact with the ADCS. So here is a large, high-level relationship diagram between the ADCS and the other subsystems. So for the payload, the ADCS will likely want some, the payload will probably demand some kind of pointing and stability of the ADCS subsystem. The propulsion subsystem will likely want some pointing to impart its difference in velocity, delta V. The solar array, so power subsystem will want some kind of solar array pointing. The thermal subsystem will want some kind of radiator pointing. The structures and mechanisms also, there are structural support alignments that need to happen potentially. Communications will care about antenna pointing. CNDH will offer timing and sensor actuator data. So you'll see that for all subsystems, ADCS included, there are intimate relationships between every subsystem where there's a give and take. So yeah, you can study that diagram. I didn't talk about how the other subsystems are imposing on the ADCS. Or sorry, how the ADCS is imposing on the other subsystems, just how the subsystems are wanting of the ADCS. So here I have an example of how the payload imparts requirements on the ADCS. you'll see here that the K2 telescope, while it's observing the night sky, wants this kind of observing trajectory, some slew like so, where these little crosses are snapshots of the astronomy that the telescope wants to take pictures of. For communications, this spacecraft is pointing into the sky while also pointing towards ground. It's using the references of the sky to figure out how to point towards the ground station. For the power subsystem, the ADCS will have to figure out how to point the solar arrays towards the sun. And there are some questions here, so I'll just get to them. In what cases would, some missions have designed the ADCS system out of consideration by assuming the spacecraft has enough solar cells so that there is more than enough power generated regardless of the spacecraft's orientation. In what cases would this happen? So if your ADCS system is not very reliable, if it's not very agile, or it has high risk of failing, then maybe you want to build in some redundancy and just cover your entire spacecraft with solar cells so it doesn't really matter how your ADCS system works. If you have enough covering, sufficient covering for redundancy, then it doesn't so much matter how your ADCS subsystem is pointing. Maybe that also frees up mission operations where you don't have to do a distinct phase where you're pointing at the sun to get power. Instead, you can do all of your operations while also guarantee that you're always charging your solar panels. And so the second part of the question is, it seems like an ADCS system would weigh less than covering a spacecraft with solar panels, therefore making it easier to get into space. So I'm just going to address this assumption right here. In fact, no, ADCS systems, if you have actuators, could weigh more. That was actually a trade study that was done within our CubeSat kit, where ADCS actuators like reaction wheels would take up immensely more mass and volume than just slapping a bunch of surface solar cells onto all sides of the spacecraft. Now that trade is for a CubeSat. For a larger spacecraft, it might make sense that the mass ratio of large articulated solar arrays are actually more mass expensive than an ADCS actuator. Is it common for the guaranteed power generation to be a benefit that outweighs lower weight? Yeah. It is. I mean, is it common for guaranteed power to be a benefit? I don't know if common's the word I would say, but it's not uncommon. Like, you just got to do your trade. At some points, power could be more important than mass. For example, if you have a huge mass budget and you can just willy-nilly add more things, then why not get more power? So I can't say across the board, but just nuanced, think about it as a trade. Is there a go-to orientation that Artemis will have while charging? For instance, will it always try to point a certain number of its solar panels at the sun while charging? I believe that on our satellite, there are four faces of the CubeSat along in a band that have solar panels. So as long as two of those faces are pointed at the sun, then I think we're Gucci. It would be very bad if one of the panels without the solar cells was exactly facing the sun. But hopefully that's not the case. I believe with that particular face without solar panels to be nadir pointing, that we will have 2 of the solar cell faces facing the sun. Okay. Also, can the ground station send any ADCS commands to the CubeSat once it has been launched? That's yet to be determined. That's up for you to write the flight software and to do the mission operations for. Okay, other ways in which the the subsystems can affect the ADCS. Yeah, I mean the thermal control, whether you have a spinner or whether you have a 3 degree of freedom attitude pointing requirement, could come from the thermal control system, like we talked about last week. For structures here, for SMAP, for example, we were talking about flexible appendages. That large antenna mesh is rotating, so the ADCS needs to compensate for that rotation by rotating the other way. And then for propulsion systems, we've already talked about you need to point your thruster in a certain direction to align it with, say, the velocity vector. Okay, don't have much time left. Last few slides. There are design considerations that you need to make for your attitude determination control system. For example, do you want your control system to be passive or active? For a passive system, you can think of a rocket where you have these fins that create spin and roll about this principal axis. For active, say you have your CubeSat and it just got kicked out of the ISS and it's tumbling. Do you want a system to stabilize the spinning of this satellite? So you'll see here, it is slowly starting to despin, and now you'll see that the green vector is aligned with the velocity trajectory. So yeah, this is active, where you're not only measuring, you're also compensating. This is passive in that you're depending on physical phenomena and static structures to compensate the system for you. This is a spectrum, so you can have, you can go from passive to active, where you can have part of your degrees of freedom being passive, and then you can also have parts of your system being active. For example, active systems can have 1 degree of freedom stability, or they can have 3 degree of freedom stability. 1 degree of freedom stability would be like a spinner, whereas 3 degree of freedom stability would be able to control all 3 of your axes. So you'll see over here, the red is what the spacecraft is passively doing, the black is what you eventually want your spacecraft to be doing, and eventually the red, the real, approaches the control of your desired. That's 3 degree of freedom stabilization. Okay, design considerations, we did that. Your computational architecture for your ADCS system could be real-time computation on board the computer or computation on ground. We talked about this in a previous slide where you can rely on your spacecraft to be really smart and have all the computing on board, or you can rely on ground station to calculate for you and then teleoperate commands. You also need to think about how computationally intense are your attitude algorithms. You can have really, really smart algorithms, but it could take up a huge data budget, and then your spacecraft is clogged up in the brain and can't do anything else. So you need to weigh that. We already talked about ADCS algorithms before. I wish I could talk through this block diagram, but we're running out of time. There is a lot of intelligence behind ADCS. This is my bread and butter. I really love this subsystem, so I wish I could talk about it more. Maybe next time. Design considerations for sensor and actuator selection. So we've seen this table many times before, but what should you consider when selecting sensors and actuators? maybe you should consider the maximum rate that your sensors can detect or that your actuators can control at. Remember, we were talking about the rate limited maneuvers. Maybe you need your satellite to actually be at a certain agility level to track, say, missiles through the atmosphere. So that's one consideration. You need to think about the drift of your sensors and actuators, the accuracy and precision of your sensors or actuators. This will eventually get you to the accuracy and precision of your pointing performance at the very end. It's a combination of sensor and actuator precision and accuracy. You need to think about the degrees of freedom that you're getting when it comes to sensors, and the degrees of freedom that you're controlling your spacecraft to. Do you want 1 degree of freedom or 3 degrees of freedom? You need to think about update rate. Your dynamics are going to be so fast or so slow, and depending on that, remember from the communications chapter, we were talking about what rate do you need to sample at for you to really know what's going on, depending on the frequency of your signal. And then you also need to think about sensors and actuators that would work in your environment. It would not make sense to bring a magnetometer or magnetorquers to Mars because there's not a magnetic field, right? So you want to make sure that you are selecting sensors and actuators that would actually make a difference in the environments that you're passing through. Okay, and I covered all the questions. So hopefully I will be well enough to see you all on Thursday.